Good morning, welcome back to my channel. This is Kaboge, and today I'll be taking you through the assistive technologies for the visually impaired. We would have said for the blind, but still, that's a general term. So what we shall be saying is specifically taking us through the innovations that have come up for the visually impaired to assist the visually impaired or the blind to make sure they have the scene narration or anything of that sort. So, of course, in these innovations, we are seeing reinforcement learning, we are seeing deep learning navigation, and other wearable systems being brought up to enhance the real-time environmental awareness for the visually impaired. This is through scene narration in form of audio and visuals, whatever you may call it. And we reviewed 10 papers. We reviewed 10 papers. But then I won't generalize them. I won't be generalizing them. What I'll be doing is I'll be talking about each paper, the methodology, the domain, and the abstract individually. So I didn't generalize them because generalizing them is more of it's like a general term, and it wouldn't be nice for the viewers. So the introduction, of course, we are seeing the visual impairment challenges and the current solutions. That's what we shall be talking about. The major problem is that over 285 million people worldwide live with visual impairment. This is a statistic according to the World Health Organization. So what could be the problem? The problem is that traditional solutions like the manual audio, let's say the brailles, let's say the guide dogs, let's say the guide sticks, all those materials are limited. And most of them are costly, like the guide dogs are costly, like in form of training them and whatever. And they're not scalable for the modern math media. So, um, speak about that, we shall now see the emerging solutions for the visually impaired. What are solutions? What solutions are coming up? And we shall go deep into them to see exactly how each one is working, what the problem they're facing, and how the proposed solution at the end, I mean, in the next video, the proposed solution, uh, how will it be mitigating the problems in these papers? So, of course, like I've told you, we shall be seeing the overview of the current research trends. That's specific about the abstract. Then, of course, from there, we shall be seeing the domain-specific problem, and then also the architecture description. So, from there, we can begin our first paper, which is the RL1. This RL1 is is an exploring model. It's an exploring model. It's an exploring model for the audiovisual reasoning. It's specific about audiovisual reasoning in multimodal large language models. So it does its thing through reinforcement learning. And to take you through the abstract of it, it introduces a reinforcement learning framework, providing reasoning in multimodal large language models using the group relative policy optimization. And just to give a brief summary of it is they actually like it makes these LLMs to make them actually reason over image plus text plus audio inputs, not just describing them. It makes them reason over them. So if they are reasoning over them, it means these multimodal models can describe audio and images, but they struggle at cross-modal logical reasoning and rarely explain how they reach to the answer. You get? So the core idea here is we use a policy learning loop. This policy learning loop, I've already told you, the group relative policy optimization, to generate the structured reasoning. It's like a think tag, and then also an answer tag. We shall be seeing them in the preceding slides. And this is the policy I've been talking about. Then also, they are trained on the AVQ AR16K dataset. It achieves a 5.24 accuracy gain. That's like an increment in the accuracy, comparing it to the previous one, and exhibits emergent self-reflective reasoning. So what is the domain? What is the domain? What is the domain problem of this? The multimodal AI faces challenges in logical reasoning. Like I'd said, it faces challenges in logical reasoning across audio and visual inputs. They struggle mostly at cross-modal logical reasoning, like I had said. And existing models underutilize cross-modal data, lack interpretability, and depend heavily on supervised learning without effective reward-driven reasoning. We shall see as we go deep, this reinforcement learning, it also has the gain. It gives gains to the model. So what is the objective of this R1? It's to build a system that comprehends and reasons jointly over audiovisual data, explains its reasoning via structured textual responses, and learns through reinforcement to enhance logic. It's basically doesn't give an answer out of the blue. It has to first think about the answer, it has to first reason about the answer, and then give you the outcome. It uses the think and the answer tags to come up with these solutions at the end. I think the challenge is identified, like I had said, it's weak cross-modal reasoning. It's biased toward vision. And also lacks transparent reasoning processes. I think it also has limitations of supervised fine-tuning, insufficient reward mechanisms to encourage the model to perform better. All right. Going on the next slide. In the next slide, we shall be talking about a methodology of this. A methodology, it begins from the inputs. Of course, we are inputting a waveform. It can be a waveform, it can be an image, or it can be a text question. So from there, the multimodal encoder, which is just here, the multimodal encoder, which is the Qwen 2.5 Omni 7B, produces fused representations, and these fused representations are now taken into the policy model. This policy model generates several candidates think stroke answer tag pairs. Like I'd say, these are think and answer tag pairs, and then we also have a reward model which assigns scores both correctness and adherence to the think and answer format. So here we have the inputs, we have the audio form, we have the image frame and text question, and this module handles raw data collection and pre-processing. For example, extracting audio features like spectrograms, resizing and normalizing image frames, and tokenizing the text question. These inputs are prepared for the multimodal encoder. We shall see in the next part. So this multimodal encoder converts each input modality into vector representations. Audio encoder, it's converted into latent audio features, and then the visual encoder converts the image into the image tokens. Then the text encoder questions tokens. These encoder signals are fused to understand the context across modalities, e.g., linking a backing sound with a doc in the image and the question. Right. And then the policy model. Now, this policy model is a reasoning generator. This component generates structured outputs using two tags. Like I said, it has the think and the answer tag. The final concise answer into two tags, internal reasoning steps, and the final concise answer using two tags, the think and the answer. So example, the audio suggests traffic noise, right? So the image shows cars. The question asks, what sound is heard? Car engine sound, of course. This format allows evaluation and reasoning. All right. So going on to the next slide. It's part of the methodology, and it shows how the reward model and the evaluator comes in. Like I'd said, the reward model scores both correctness and adherence of the other tags of ours in that format of think and the answer. So after generating multiple candidate responses, the reward model checks answer accuracy and format validity It calculates a reward, combining both aspects, forming the feedback signal that drives learning. This is specifically for learning. Of course, if you reward something, you give it morale of learning better. So after that, the updated NCNOC R1 7D model. It's after reinforcement learning updates, the model becomes smarter and more self-reflective. This is because of the rewards that are assigned to the model. It learns to double check its reasoning, and it achieves an accuracy of 85.77, like I told the increment of 5.24%, and produces clear reasoning with fewer hallucinations. Then this next one talks about the policy optimization, which is the group relative policy optimization, the GRPO. GRPO compares multiple responses from the same model instead of a fixed baseline, identifying the better response within a group advantage to improve the policy. This method is more stable and efficient than the other methods. Okay. All right. This is just a simple explanation of what I've been talking about. We have the inputs. We have the inputs here. We have the inputs processing. Of course, we are having three inputs. There can be three inputs: the audio, the image, or the text. Then we go to the encoder model. The encoder model, of course, like I explained from the encoder model, we can go now to the police model. This police model, it could be the GPRO. Then from there, we have the reward model. Reward the model to help it keep learning, to moralize it and help it keep learning. Then after that, the model is updated. It's updated to is learning in the future, right? So the next paper is about navigation path detection using fully convolutional layers. This paper uses a FCN, fully convolutional layers, to perform pixel-wise segmentation of a walkable path. So a visually impaired user can know where it's safer to step. Okay, so let me go through the abstract. It introduces a deep learning approach to assist visually impaired individuals by identifying walkable path, like I said, through pixel level semantic segmentation using RGB images. It gets an image, segments the image into pixel patches, right? To at least tell the person, the visually impaired, which place is safe and which one is not safe. Then the problem being addressed here is it addresses the challenge of detecting safe walking path without relying on light texture or depth, because we know these people they don't see, so they have that inability of see the light. They can feel the texture, they can see the depth of sensors, but then it addresses that challenge. And then existing systems depend on handcrafted features, environmental assumptions, limiting reliability. This method automatically and accurately identifies obstacle-free navigable areas using only standard RGB cameras, enabling independent navigation aids for the visually impaired. Right. So on the methodology, what do we have on the methodology? Of course, we have the input. We input a single image, which would be an RGB image. It's normalized, it's resized. Then we got the convolution layers. Now the convolutional encoder extracts hierarchical features. It's more of a pooling, reduced partial size, right? Then from there, we have the convolutional, this is like more of upsampling layers, reconstruct dense pixel-wise predictions, all right? Those are the pooling layers, the gray blocks. Then from there, we are having the skip connections, or assumption blocks. These ones merge early high resolution features with deeper semantic maps. Of course, we're using the FCN 80 style to preserve boundaries, right? So the output is a segmentation mask classifying each pixel as navigable or non-navigable. And this in the end helps the visually impaired users to know which place is safe and which place is not safe, right? Okay, so the result in the end, of course, the result is it's a 91% pixel accuracy on tested datasets, robust to different lighting and textures. Like I'd said, it's not dependent on that lighting, and the textures. All right. So the strength and takeaways we can have in this is a single RGB into a fully convolutional network pipeline avoids expensive sensors and generalizes well. I- there's nothing like a lot of sensor data and all that stuff. So in the end, it's that strength that it has. It doesn't use a lot of sensors, right? So this is like this is the third paper, yeah. This is the third paper. A third paper, it's a smart assistive system for the visually impaired people. It's a smart assistive system for the visually impaired people, but it's focusing more on obstruction avoidance through object detection and classification. It's more of the previous one that I've just been talking about. And this one, it's more of object detection and classification. All right. So the system, it's a wearable, low cost effective system mounted on a walking stick using a Raspberry Pi. This is like a processor. It's like a microchip. Then it has a camera. It also has a ultrasonic sensor. This is for detecting objects. And then the servo motor and also the Arduino to aid obstacle detection and classification. Then the technical approach, we have it combines Viola Jones and TensorFlow object detection algorithm with ultrasonic distance sensing to identify obstacles and classify objects in real time. Then the user alerts. How does the user get alerts? It fuses visual and distance data to provide audio and beep alerts indicating obstacle location, front, left, right, and then verbal identification. It can be through the Bluetooth, it can be through anything to alert the user about identified the detected objects, right? So the domain challenge and solution here, it addresses the need for a portable, accurate, and lightweight navigation aid for visually impaired users that works effectively with outdoors without bulky or expensive things, right? So uh it's like a low-cost wearable system that fuses a camera-based object detection using ultrasonic distance sensing and gives audio or beep alerts to the users in case there is any obstacle ahead of them. And the problem here, there is a need for a portable chip system that both identifies objects and tells users how close obstacles are, right? So I think from here we're going to a methodology, right? Okay. The methodology, we are having a lot of things. We're having the input components. We are having we are having the hardwares, we are having the vision pipeline, we're having the distance sensing, we're having the tensor fusion and the feedback. So taking through all that, we are having we are having let me first take you through the hardware. The hardware, of course, we're having the Raspberry Pi 4P, we're having the camera, we're having the Arduino, we're having the ultra sensor, like I said before in the previous slide. We're having the servo sensor, we're having the buzzer or speaker. This is to alert the user, right? Then from there, we're having the vision pipeline. The vision pipeline, we are having the Vela Jones for quick features, right? And then the TensorFlow object detection for classifying the labels. And then from there, we are having the distance sensing. How far is the obstacle in form of distance? We have the HC SRO4 ultrasonic sensor mounted on a server to scan left, center, right. Okay? Scanning for obstacles. All right. Then from there, we have the sensor fusion. Now the PI integrates object labels and distances from Arduino to decide alerts. All right. Then the feedback now, it's a directional beeps. 1 to 3 beeps indicate obstacle side. Like you can say one beep, one beep indicates an obstacle in front. 2 beeps would indicate an obstacle on the right. 3 beeps would indicate an obstacle on the left, like that, like that. All right. So this is basically about what I've been talking about. So I won't go through all this, right? So the next paper is the IoT-based match shoe for the blind. This would work in the same way, like it's the same architecture like the previous one, because this is now IoT based. Now here, an IoT smart shoe combines ultrasonic sensors and a piezoelectric energy harvester to detect obstacles and reduce battery usage. Right? So the problem here is conventional aids miss elevated obstacles and suffer battery limitations. But then we are seeing in this sense, we are coming with power solutions, and it needs hands-free and long-range awareness, right? So this let me take this to the domain-specific problem. Visually impaired individuals face challenges in independent navigation, especially outdoors. Traditional walking sticks have limited detection range and cannot sense elevated obstacles. You get? So, leading to a dependency on others and safety risks. Frequent battery charging in assistive IoT devices also limits usability. But then here, in this methodology, we are going to show you how we mitigate this challenge of battery charging, right? So the solution objectives, we are to develop a low-cost, energy-efficient, real-time obstacle and obstacle detection and alert system, combining a smart shoe and smart glasses. Smart glasses are for those obstacles that could be elevated, and then the shoe could, the smart shoe is to solve all those problems, or I mean, all those obstacles, to detect all those obstacles that are at least underneath. Okay. So without manual operation, supporting safe navigation both indoors and outdoors for the blind users. So the smart glasses now would come in handy, let's say indoors, and then the smart shoes would come handy, let's say for the outdoors, right? Okay. Now, the next one, we are explaining the architecture, of our system, right? Explain the architecture. Of course, we are having a smart shoe now. Multiple ultrasonic sensors, the server suite, the Arduino microcontroller, the buzzer, the vibrations for haptic and audio alerts. Then also having a smart glasses module. These ones are head level for head level sensing and to detect obstacles above the shoe range, like I'd said. And then you're having the piezoelectric panels. These ones are in the soul harvest energy during walking to recharge batteries. Now, this is a solution that handles the battery draining. All right, we are having the piezoelectric panels for recharging the shoe, the battery, the shoe, right? Then you have the IoT stack that we are having here. We are having the Bluetooth, we are having Zigbee or Wi-Fi to pair shoe and glasses and upload the telemetry to ThinkSpeak for analysis. This could be like a cloud server somewhere, all right? So we are having a lot of IoT that we are using. Then we're having the smart shoe module, which has the ultrasonic sensors to detect the object, the servo motor, the Arduino Uno, which acts as the microprocessor. We're having the piezoelectric panel, which is like a charger of the battery. And then you're having the buzzer, which is for beeps, telling the person, you know what, there is some obstacle in front of in front of you. It could be in form of beeps, beep, 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 like that. So the smart glasses module, this also has ultrasonic sensors, it has a radar setup, it has a Bluetooth headset for the connection, for communication between the user, between the shoes and then the user, like transferring that. Then we also have it detects objects at head level, like I said, and communicates with the shoe module to coordinate alerts. This is because everything's now connected to the Arduino Uno, and then the impulses, the communications are shared between the shoe and the glasses via the Bluetooth sensor, right? And now the next slide, it shows the architecture. Of course, we are having the user, we are having the shoes, we are having the piezoelectric for the battery, which is also attached on the microcontroller. We are having the vibrating motor, also attached on the microcontroller, which is the Arduino Uno, the buzzer, all that, they're all attached on the microcontroller, which is the Arduino Uno in this sense. And then the ultrasonic detector, which is to detect objects, in whichever range they are. And then if an object is detected, the buzzer sounds, and the person can easily tell and know that there is some object in front of me and I have to take this, just dodge obstacles. Okay. The fifth paper we reviewed is a smart jacket for navigation. It's also for the visually impaired. In the other domain, we are operating an assistive technology for visually impaired people through wearable electronics and providing them navigation aids. Right. The abstract here is that this paper proposes an efficient, reliable, and low-cost wearable smart jacket designed for visually impaired individuals. By embedding sensors into the jacket, the user can take obstacles and navigate safely. This prototype achieves 98% accuracy for obstacles within 200 centimeters and operates on low power, making it suitable for real-time navigation. Right. Which problem are we solving here? According to the World Health Organization, 90% of information is received through vision. Yet, 285 million people, like I said in the beginning, worldwide are visually impaired. Existing solutions like Whitekins, guide dogs, and whatever, they have their own limitations. Can detect only upon physical contact and can cause user fatigue due to consistent notifications. And then the guide dogs are expensive, in terms of training them. They require training and serve only 3 to 5% of the blind population, right? So there is a need for an affordable, lightweight wearable device that detects obstacles and provides safety for the user. Okay, so going on the methodology, going on the architecture, the methodology of this, we are having sensors. It's still the same thing from, that's what I said in the beginning. I never wanted to generalize everything because at least most of them have the same architecture, you see. So now, like the previous one, we also had sensors. Then these sensors are embedded like in a sensor unit. We also have the smartphone unit to inform the user about obstacles. Then we also have the performance and feedback feature, right? So I take you through the methodology. We have embedded ultrasonic sensors, the front and back, that are embedded in the jacket. We have the 80 mega microcontroller, the HTC05 Bluetooth, and then the microcontroller reads distances and sends data to a smartphone, which runs audio output logic. Okay, and then the alerts are spoken instructions like front left or vibration audio cues. And then we have the modular design, which allows extending functionalities. The GPS, the heart rate, to mention that I feel. That's part of the performance and the features. So this is the architecture of the system shown here. Okay. Then this is the architecture I've been telling you about. We are having these batteries, the power supply, and we're having these three units: power supply unit, the processor unit, and the communication system, all at and the sensor interface, all attached on the Arduino Uno, which is like the processor. And then these communications are also in the smartphone. It could be via audio, it could be via vibrations, to inform the user about, about the obstacles. Okay. Then now the sixth paper, it's a Visual 8. It's a Visual 8 plus. Visual 8 plus. Visual 8 plus assistive technology. Assistive system with tiny ML, enhanced object detection and scene narration. All right. So here we are having it's like more of a distributed work. Microcontroller, tiny ML models for person detection, Raspberry Pi for object detection, and then a server for heavy captioning. Of course, we are captioning now. This is now more of live captioning. Get an image, caption it, transfer text to speech, like that. Okay. So it's a wearable assistive system for visually impaired individuals that integrates tiny ML and Edge AI for real-time object detection and visual scene narration. Small models run on microcontrollers for person detection, large models on Raspberry Pi handle object recognition, and then complex image captioning is processed on a server. The system delivers audio feedback to enhance user awareness, of the obstacles of the environment. Then the domain source problem. Usually, impaired users face challenges in self-dependent navigation and scene narration and scene interpretation. Existing solutions often depend on bulky hardware or cloud processing, causing delays and limiting portability. So the Visual 8 Plus addresses these issues by providing a compact, portable system capable of on-device detection and narration with minimal reliance on cloud resources. All right. Okay. So how is the architecture of this system? The architecture of this system is uh, the architecture of this system um it's we are having wearable glasses with microcontrollers and a camera. So the camera takes pictures, it takes pictures, then uh it captures in the pictures and the live feed. All right. So after this live feed, uh after live feed, then now the Raspberry runs TensorFlow Lite, MobileNet, SSD for 80 object classes. When richer captions are needed, images are uploaded to a server that runs an encoder decoder captioning model with attention. So that's how we get our captions. Then from getting our captions, these captions are now translated into speech from the server to the user, right? And the user now can have a clear narration of how the scene looks like and how everything is. You see, so this is specifically what I've been telling you about. The camera captures the images. After capturing the image, then the microcontroller processes these images, and we have the person detection module. This person detection module, it's like a visual wake word that runs a tiny mobile net based model for continuous person detection. And then these images are now sent to the Raspberry Pi, which does the object detection and recognition module and sends them over the internet to the server. This server is where the live captioning now takes place. All right. The live captioning now takes place here. And then the captions are now transformed into speech using the text to speech models. And these captions are now read aloud to the user via, via the speaker. It can be headsets and whatever. Okay. Then the seventh paper we reviewed is I reviewed is a smart Google system for the visually impaired. Right? You're having smart goggles. This is also, like the previous one I've been talking about, only that for it, it's it uses a PI camera. It also has the CNNs. It uses a stack of CNN and LSTM to both detect objects and generate short scene descriptions, outputting audio over Bluetooth. Specifically, it's more of like what I've been saying in the previous slide. But to explain shortly about it, the users need concise and continuous narration of objects and scene context. Get so which methodology? Which methodology are we using here? Of course, the hardware. The hardware we're having the Raspberry Pi, we're having the camera, and we're having the Bluetooth headset. What else? So the software, we're having the OpenCV for capture. We are having TensorFlow Lite for object detection, and the CNN for features, to get the features of the scene. Then we also have the LSTM. This is the decoder for sentence generation. So the whole flow now, you get an image. After getting the image, you extract features from the image. You get text data of the image. Then this text data is now transferred into Scene Narration via Bluetooth. It can be through headsets, and the user can have a picture of the whole environment. Yeah. This is a simple narration of the components, the hardware components, the software components, the data sets, and then the functional modules, same architecture like the previous one. Yeah. Then the eighth paper, it's about the audiovisual translation models for visually impaired users of interactive television. In Portugal, most programs in Portugal, they don't have live captions. on TV. They don't have live captions. And these ITVs are very expensive for the normal person. You get, they're very expensive for the normal person. So what do we do now? We have a two low-cost ITV accessibility model, voluntary user models, and have voluntary user-generated audio descriptions and automatic subtitle to speech reading. Here we get voluntary people. They give us the captions. They give us the captions of the programs, and then the visually impaired can now perceive the programs in their own sense without relying more, without minding about the cost, without minding about the programs, because it was one program in Portugal that was using only that. So if you're having all the programs having that thing, that technology, that means we are helping these people to at least also feel like they're not left out of the community. So the architecture is we are having a voluntary AD model. Volunteers record synchronous AD via web or mobile app. Then they upload to an AD repository. And then the ITV app pulls user-selected AD track for playback. I mean, it's more voluntary. Every person, we have a model, we voluntarily give it out. Then the people record the captions or record audio, and then we use this audio to help train our ITV programs. Then you have now, the next thing is automatic subtitle reading model. You have the SRT, or subtitle files are fed to a text-to-speech engine, TTS engine. Then audio stream synchronized to broadcast and consumed via an ITV app. Simple as it is. Then I'll have the strength and the takeaways. It's practical. It's practical, and it has a scalable approaches. One human-centered, like it's voluntary, it's low cost, and it has one automated thing, which is the text-to-speech, TTS, which are both integrated into the ITV. Right? Okay. Now, this is the architecture. We have the volunteers. They do the AD recording. These AD recordings are now uploaded to the database. Then from the database, we can now feed this content, this AD content, into the ITV for the viewers. Okay. The next paper, it's about it's called the vocal eyes. It's enhancing environmental perception for the visually impaired. All right. So the problem here, before that, we are seeing that vocal eyes are fine-tuned and quantized flawless to run on Jetson Orin, nano producing context-aware captions plus distance estimates and audio alerts. All right. It's a real-time assistive system providing audio description using a quantized and fine-tuned flawless to visual learning language model on NVIDIA Jetson or in Nano for efficient edge processing, right? Then the core functionality, it captures live video frames, generates contextual scene descriptions, and distance estimates for objects and pedestrians, enhancing situational awareness. So the design focus here, we are focusing on optimizing for low latency, high efficiency, and high offline operation without cloud dependency. We have seen the former paper, it was relying on the cloud, but this one doesn't need a lot of cloud dependency, enabling portability and independence in diverse environments, right? So we are on the audio feedback. It utilizes parallel TTS, text-to-speech mini, a lightweight text-to-speech engine, delivering customizable real-time audio feedback with adjustable tone, pace, and voice style. It's more like Siri. All those AIs, that have adjustable voices. you decide which voice you want, a woman, man, child, any voice you want. So the methodology, the part of the methodology, we are having we are having the live video capture. 3 frames at we can say 3 frames at an interval of 0.5 seconds, or audio updates every 5 seconds to balance latency and clarity, right? So captures live video, breaks into 2 frames spaced by 0.5 seconds, 3 frames in total. Then from there, we are having object detection and distance estimation. So now here we use now Florence 2 model to accurately detect objects and estimate their distances. Right? Then from there, we are having the audio updates. It provides clear audio updates every 5 seconds to keep users informed. Then the last one on the system design, we are having a real-time optimization. It's optimized for real-time inference on Jetson, Orin, Nano to ensure efficient performance. Then this is the system design. It's basically what I've been talking about in the previous slide. Okay. Then we also have our 10th paper, which is the last one. This one, it's enhancing viewing experience. It leverages a vision transformer and BERT for audio description. It has the same architecture, almost the same architecture like the previous 2 methodologies I've been talking about. And this work builds an automated audio description pipeline using vision transformers to extract visual context and BERT to produce coherent textual narration that can be converted to speech. Right? Taking through the abstract, this paper presents an automated audio description system that enhances multimedia accessibility for the visually impaired. It uses natural language processing, NLP, and machine learning. And then the system automatically generates audio descriptions for videos, films, and TV programs. Okay. So the proposed approach, we are having scene segmentation. We divide multimedia into visual context, and then we are having object recognition. It detects and classifies objects in each scene. The natural language generation converts recognized visual data into coherent spoken descriptions. Okay. Taking the architecture design, we are having data preprocessing, which is the first thing. It utilizes the Flickr 8K dataset with images and 5 human written captions per image, including resizing, cropping, and data augmentation. From there, we're having the vision transformer, which splits images into patches and applies transformer encoders to capture spatial dependencies, extracting key visual features. Then the third one, we are having the BRG transformer. This one processes textual data with soft attention to capture semantic meaning and context fine-tuned for generating coherent captions, right? Then the next thing is sequential feature processing, which combines vision and text features to produce structured narrative text, converting it into audio via text-to-speech synthesis. All right, then after that, we shall be having the evaluation metrics, assesses performance using the build and feed scores, ensuring accurate and fluent description of visual scenes. And the design architecture is there. Like I'd said, the design architecture, we're having data and pre-processing, which is the Flickr 8K dataset for data augmentation and normalization. Then from there, we are having the vision model. The vision model divides the picture into patches, the image into patches, And these patches are now transformed into embeddings from the BERT. Then from there, we have the sequence processing, which combines the visual features with BERT encoder, then representations, and then decode into human readable captions. Then the result is a VIT plus BRT produced more coherent, fluent captions than traditional CNN and LSTM baselines, right? So now, from here, after the speech synthesis and the voice rendering, this audio is given to the user. It can be via any Bluetooth or any wearable that the user will be having. So that's my presentation. Thank you, and please don't forget to follow, like, and subscribe this video for more updates about machine learning, about technology. Have a good day. Thank you for watching.